Hello and welcome. In this video, we're going to take a look at a very specific kind of first-order differential equation. The good thing about this kind of differential equation is that we can solve it using just good old integration techniques. It's a very good use for learning all those integration skills. And we've seen a couple examples of first-order differential equations already in previous videos, things such as natural growth, where the rate of growth of a population is proportional to its current size. Or maybe you've taken a look at a couple other examples like Newton's law of cooling, where the rate of change of temperature is proportional to the difference between its current temperature and the ambient temperature, although in the opposite direction. Now, those are just a couple quick examples. There's plenty of other examples that are first order differential equations. Some of them are separable and some of them are not. But a separable equation is what we're going to be looking at today. So let's start off with a definition. Remember that a first-order differential equation is something where we have, let's say, y is a quantity, and we have a relationship between the derivative of y and y itself. Now, we could write that in the form of dy by dx equals f of xy, where f of xy is a function of two variables. That's just some sort of combination of y, which is our dependent variable, x, which is our independent variable, and then whatever other algebraic manipulations and constants we have on that right-hand side. Now, a first-order differential equation could be separable. We say that that first-order differential equation is separable if that function of two variables can be factored into two single variable functions, f of x and g of y. So each of those can be just some expressions, but they can only involve one variable, and they are factors. That means that we can rewrite the right-hand side of this as f of x times g of y. This gives us a little idea about why it's called a separable equation. Now that we have separate factors, we can use division and multiplication to separate variables on one side and the other side of the differential equation. Here's what I mean by that. Let's take that same differential equation, and let's say that all of the x's are going to be here in blue for a moment, and all of the y's are going to be in red, and I want to get everything involving x on one side and everything with y on the other side. So I'll just divide both sides of this equation by g of y, whatever that expression is, and while I'm at it, I'm going to multiply both sides of my equation by dx. Those are differentials, so we're splitting up dy by dx. We're thinking about a small change in y with respect to a small change in x, and we're splitting that up. So we have a small change in y over g of y equals f of x times a small change in x. Well, that is a perfect example of being able to now integrate. To get rid of our derivatives, we're going to do the inverse operation here and integrate both sides. Now, when you integrate the left-hand side, I have no idea what that expression is. G of y could be just about anything, so I have no idea what it would be in general, but this might be some sort of integral that we can apply the appropriate integration technique to. And then the same thing on the right-hand side, I have no idea what this expression is, f of x. Hopefully we can integrate the right-hand side. If both of those are fairly straightforward integrals, then we can get some sort of solution. Remember that the solution here is hopefully we have y equals some function of x and y. But there's going to always be a constant of integration. Remember that when we have an integral that is indefinite, we're going to have a constant on this side. So we might say plus c1 over here. On the right-hand side, we're also going to have an indefinite integral, so that's going to be a constant as well, maybe plus c2. But here's the trick. If I have c1 on one side and c2 on the other side, it would make a little sense here if I were to just subtract c1 from the right-hand side. And I'll have plus c2 minus c1. That's just a constant minus a constant. Why don't we just let c equal to c2 minus c1? That means that when I do the step of finding the two antiderivatives, I'm simply just going to have a plus c on the right-hand side. And I only need one arbitrary constant. And remember, keep in mind that the general solution to a first-order differential equation should have one arbitrary constant. This will help us to get the general solution, and at some point in time after we've finished getting the solution, We can always take some other condition, plug it in, and try to find out what the particular value of that constant needs to be. All right, so let's do a couple examples and see if we can come up with a solution of the form y equals some expression to a differential equation that is separable. In this first example, dy by dx equals 3x squared y squared, well, we can see that that is easily factored into separate functions of x and y. Actually, it's already factored for us. It's just a matter of where we want to place that 3. It doesn't really matter too much. Why don't we take both sides, divide by y squared, and take both sides and multiply by dx? Well, that will split it up into two functions there. We have a function of y, which is 1 over y squared, and we have a function of x, which is 3x squared, and we're going to integrate both sides. That gives us the antiderivative of 1 over y squared, which is negative 1 over y, and the antiderivative of 3x squared, which is x cubed. But since both of these are indefinite integrals, you can imagine there's a plus c1 on the left and a plus c2 on the right. But if we just let capital C be equal to c2 minus c1, then we only need a single arbitrary constant on the right-hand side. At this point in time, to get a solution for y, we'll just take the negative reciprocal of both sides of the equation. And that gives us y equal to negative 1 all over x cubed plus our arbitrary constant c. In this second example, you can see there are two separate functions, but they form a quotient, not a product. We have y over x squared plus 1. We can still separate the variables just by taking both sides of the equation multiplied by dx and both sides of the equation divided by y. Now keep in mind, in both of these examples, we must have that y does not equal to 0 in this first step. Now let's see if we can integrate both sides of that equation and get a solution for y. Now, the antiderivative of 1 over y for all values of y not equal to 0 is the natural logarithm of the absolute value of y. On the right-hand side, you might recognize 1 over x squared plus 1 as being the derivative of arctangent x. Now remember, we can combine both arbitrary constants into 1 and just have plus c on the right-hand side. Now we need to solve for y. Let's start by getting rid of the natural logarithmic function by writing this in exponential form. That gives us the absolute value of y equal to e to the power of arctangent x plus our arbitrary constant. Now, getting rid of the absolute value, we have to consider the expression on the right, either positive or negative. Now, there is also another trick we can use here, and that is a property of exponents. E to the power of arctangent x plus c, that can be written as e to the power of arctangent x multiplied by an additional exponential function e to the power c. Since e to the c is nothing more than a constant value to the power of a constant, why don't we replace that with a? And a can also be positive or negative. So we'll just have the solution y equal a times e to the arctangent x, where a is a positive or negative constant equal to plus or minus e to the power c. Now going back to that restriction, y cannot equal 0. If you take a look at both of these equations and try to set them equal to 0, you won't find any value of x that will allow that. So it kind of makes sense when we do that first step of separating the differential equation, that restriction is held true right the way through to our solution. Now that we've got both of these solutions, let's see if we can visualize the differential equations using their direction fields and see how these solutions are the family of curves that we get from different initial conditions. So here I've got that DE tools package loaded up, and our first differential equation, the derivative of y with respect to x at x, is equal to 3x squared times the value of y at x all squared. Remember that y is dependent, so we're treating y as a function of x. And we have some initial values here that I'll plot here in a moment, but let's just take a look at the direction field. Now, I've only plotted this from -3 to 3 for y and x, just because you can see that pretty much anywhere outside of this region around the origin, everything is pretty much just vertical. More interesting behavior just happens in this little local area. Yeah, you can see here some interesting behavior. We have very vertical little directions anywhere outside of the origin, but we have sort of more horizontal slope on the x and y axes. All right, let's try this initial value here and see what we get. Okay, well, there's that interesting behavior. You notice how y cannot equal 0. We actually have our function with a horizontal asymptote, but we do end up with a slope of 0 when x equals 0, which is what we would be expecting from our differential equation. And then as x and y increase, this thing gets pretty much vertical. That should correspond to the solution that we get. And we can do that very easily here using the dsolve command. Let's solve that differential equation for the function y of x. Sure enough, 1 over negative x cubed plus some constant is equivalent to our answer of negative 1 over x cubed plus a different constant. I guess RC and Maple's C1 would have to be opposite sides. Now, what if we wanted to plug that initial condition in? If we want to change this dsolve command so that it uses our initial condition, we'll just need to create a list. So we have square brackets here, and we have two items in this list. The first equation is the differential equation, and the second equation is our initial condition. And we'll make it solve both those equations for y of x. And we have negative 1 over x cubed minus 1. So that must be our constant. Let's see what the graph of that function looks like. We'll plot that over the exact same window, x equal negative 3 to 3 and y equal negative 3 to 3. And I know there's going to be a discontinuity when x equals 1, so I don't want to actually graph that vertical line. Well, there we go. That is exactly the same curve that our solution should take if it is following our direction field. Now, what about that second differential equation? Well, here is repeating that process with the second differential equation, y over x squared plus 1. And we see here our direction field with the initial value problem here where y of 0 equals to 1. And we can go ahead and get the dsolve command to confirm our answer. Here is the general solution, a constant times e to the arctangent x, and the solution to the initial value problem where y of 0 equals to 1. That's simply just having that constant equal to 1, I guess, e to the arctangent x. And that would be the equation of this blue curve. Now, let's go back and take a look at a couple of our famous first-order differential equations and see if they're separable. And if they are, then we can come up with a general solution and also particular solutions. Let's start off with our natural growth model. The rate of change of a population is proportional to its current size. But let's also have an initial value problem. Let's say that the initial population is p naught. Now we say that k is the relative growth rate, and p naught is just some positive constant, which is our initial population. Now you can see that this is separable. In fact, there actually is nothing to do with t on the right-hand side, so it's pretty easy to separate this. Dividing both sides of that equation by p and multiplying both sides of the equation by dt, that gives us dp over p equals k dt. And now we can integrate both sides. Well, that gets us the natural logarithm of the absolute value of p equal to kt. Don't forget to put some arbitrary constant plus c in there. Now we need to solve this so that we can evaluate the population at any given time. So we need to get this as an expression of the form p equals something. Let's convert this to exponential form. Absolute value of p equals e to the kt plus c. And we can do this nice little trick where e to the c is just some constant. We've seen this solution before. P equals a times e to the kt. Or in function notation, population at time t equals a e to the kt. And a is plus or minus the value e to the power c. Now what about that initial value? Population at time equals 0 is equal to p naught. We can plug that in and get a particular solution. Setting the population equal to p naught and time equal to 0, then we end up with e to the power of 0, which gives a equal to p naught. So the particular solution to the differential equation for natural growth is p naught times e to the kt. Now, let's take a look at Newton's law of cooling. It's actually very, very similar because of that same sort of idea of having a rate of change be proportional to a current value. With Newton's law of cooling, we have the rate of change of temperature is equal to negative k times t minus ts. And capital T, temperature, is a function of time, but k is a constant, which is the relative cooling rate, and ts is a constant, which is the temperature of the surroundings, or temperature of the environment. Let's suppose that the initial temperature is T naught. Now, that could be positive or negative. Let's see how we can separate this equation and solve this much like our natural growth equation. If we take both sides of the equation and divide by T minus Ts, and multiply both sides of the equation by dt, we've already got it separated. We'll integrate both sides again, and the derivative on the right-hand side is much the same as natural growth. Just we have a negative sign now. However, on the left-hand side, we'll have to maybe just use a quick substitution rule and let u equal t minus ts. Well, that gives us 1 over u du, which has an antiderivative of natural logarithm of absolute value u, and putting our substitution back in, this gives us the natural logarithm of the absolute value of t minus ts. From here on, we can follow all of the same steps to get to a solution of T, temperature, at time t. Following those steps, we end up with the general solution, temperature at time t is equal to some arbitrary constant A times e to the negative kt plus Ts. And A here is just some constant that is equal to plus or minus e to the power c. Now, let's use that initial condition, plug in an initial temperature of T naught and a time of 0. Once again, right away, we have e to the power 0, which is equal to 1. That gives us T naught equals A plus Ts, and so our arbitrary constant A must be equal to the initial temperature minus the temperature of the surroundings. We can plug that in and get the particular solution to Newton's law of cooling. T naught minus Ts all times e to the negative kt plus Ts. Hopefully this makes a lot of sense, because if you think about taking the limit as t goes to infinity, then the value of e to the negative kt approaches 0. And temperature approaches 0 plus Ts, which means eventually we're just getting closer and closer to the temperature of the surroundings. Well, there we are. That's the separable equations method. It has to be a separable differential equation for you to even try this technique. The moment that you have a differential equation involving several terms, well, you might not be able to factor that into separate functions and use this technique. There are other techniques for that. You might be able to see several terms that are linear in some sort of fashion, and there's a method for that too. The moment you see a second order differential equation, though, then things get a little bit more complicated. But the goal here is to take a couple basic relationships between the rate of change of a quantity and its current quantity and see what the solutions look like. Now we have at least some capability of being able to solve them ourselves. So you take this model and you see if you can solve that for a function. And once you get the function, you just plug in time or you plug in x and you can find the value at any given time, which is, very practical. So hopefully this gives you a little bit of an overview of just kind of scratching the surface of differential equations. And just imagine that there are a lot more tricky methods out there to come if you're looking at maybe more intricate applications. Thanks for watching, and I'll see you in the next video.